Okay, in this video I want to talk briefly about this idea of what's called differentiable. So we've talked now about finding derivatives. And so we say that for any function f is differentiable on some interval if its derivative exists for every value in the interval. Every value in the interval. And so this is in the notes and you can follow along. I'm going to go through it pretty quickly here. But if we have a function like x to the 2/3, we want to know when is it differentiable. Well, the derivative, using our power rule, would be 2/3 x to the negative 1/3, which we could rewrite as 2 over 3 cube root of x. So then that derivative process carried through perfectly. So at this point, we're asked, kind of faced then with the question of, is there any time that that won't work? And yeah, it won't work. If x is 0, we would be dividing by 0. So 0 is outside the domain of the derivative. 0 was perfectly fine as a point, as a value in the original function, but it's outside the domain of the derivative. And so therefore we would say the original function f is not differentiable at x equals 0. Now, one of our main focuses is, well, what does that look like? What does non-differentiability look like? Well, here's our x to the 2/3 function. Here's our x to the 2/3 function. It's not differentiable at 0. And what I want you to see here from this picture is that we have this sharp point coming down. Right? The graph makes a sharp turn. The graph makes a sharp turn. And so it's not differentiable because of that sharp turn in the graph. The graph needs to have gradual turns. Everywhere else, it's okay. If you look at the limit from both sides as far as the derivative goes, it would be approaching the same value. But here it would not be because of this sharp turn. So that's one possibility. You also get that same thing, that sharp turn, with the absolute value function. That sharp point coming down to a point. Derivatives from this way are approaching -1 because it's y equals negative x when you're less than 0. Derivatives from this direction are approaching +1. So again, the two sides don't agree, and that is going to result in some kind of sharp turn in the graph. Some kind of sharp turn in the graph. Another possibility is if we look just at the cube root of x. Just at the cube root of x, if you go through and find the derivative of that, it'll be 1 over 3 x to the 2/3 power. And so we're having another division by 0 issue here. And what's going on in this problem is your tangent lines are approaching an infinite point. You have tangent lines that are approaching infinity from both directions. And again, that kind of behavior can't happen. So if you have something like that, it's also not going to be differentiable. And the other possibility is something like this where we have vertical asymptotes. And of course, the actual function is undefined. So, if the function's undefined at the point, then obviously we're not going to have a derivative. And so that would be not differentiable as well. The final example I want to look at, and you can follow this in the notes a little more closely, is a piecewise function at the switching point here at x equals 1. And so if you look at the graph, you got to zoom in a little closely. There is a sharp turn. It's not as sharp. It's not as sharp as the two we looked up above with absolute value and that x to the 2/3. But there is a sharp turn here. The slope on the x squared function at 1 is 2. So the tangent lines on this side of 1 would have a slope of 2, whereas the ones on the other side have a slope of 3. So it is another sharp bend. If you zoomed in a lot, that turn is there, and there is that point. It's just a little bit harder to see. But those are really the times when we can have things not being continuous. Again, please look over the notes where you can see that a little bit more clearly. And the last point that I wanted to point out here is this idea right here is a very important point. If the derivative exists at the point, then f is got to be necessarily continuous. Right? And this kind of makes sense. If the derivative is approaching the same direction on both sides, the same slope on both sides, then our function has to be continuous. So if the function's differentiable, at that point, then f has to be continuous. So differentiability implies continuity. But continuity, in the example up above here, shows it doesn't go the other way. This is a continuous function, but it doesn't have a derivative at x equals 1. Right, so that's a quick rundown. Again, please look through those notes and look through those examples a little bit more carefully. That just gives us an idea about this idea of what it means for something to be differentiable.